Okay, we're going to be talking about Newton's law of cooling. So let's take a look at an example here. An object at 1500 degrees Fahrenheit is placed in an environment of 90 degrees Fahrenheit. 1 hour later, the object is 1120 degrees Fahrenheit. We want to know what is the temperature of the object 5 hours after the initial exposure. So the formula, the differential equation that we're going to use is d of t, capital T, which represent temperature, divided by d of t, lowercase t, which represents time, which is equal to a constant k times the quantity, a temperature minus 90 degrees. Now, if we wanted to then apply the separable equation rule, we can divide both sides by t minus 90 degrees and then multiply both sides by dt. So over here, if we take the integral of both sides, we would have the integral of 1 over t minus 90 degrees dt, and that's equal to the integral of k dt. So now we would get is, if we take the antiderivative, we have the natural log of t minus 90, which is equal to k times t plus c. Now, in this scenario, in previous examples, we can use the properties of logarithms. So we can do that. But in this scenario, since we know what the initial value of t is, and we know that t is equal to 1500, the temperature, we can go ahead and plug that in to solve for c. So since we know that t represents 0, and we know that the temperature is at 1500, then we would get the natural log of 1410, and that would equal c. So now we have c, and now we can replace the variable c with what we got here into step 2. So in step 2, we have the natural log of t minus 90, which is equal to k times t plus the natural log of 1410. So now in the problem, it's saying that 1 hour later, the object is 1120 degrees Fahrenheit. So now we're going to plug those values into the function. So we know that t represents 1, and the temperature is 1120. So if we subtract those, we get the natural log of 1030. And then we can subtract the natural log of 1410 to both sides, so we can solve for k. And now keep in mind here that the natural logarithms, when you subtract, the property that you use is division. So it would be the k would equal the natural log of 1030 divided by 1410. Now in step 3, we have the natural log of t minus 90, which is equal to the natural log of 1030 divided by 1410, which is what we solved for k. So in this scenario, now that we got k, we can then go ahead and plug that in, which is what we got here. And so from here, we can then solve the temperature, because the question in step 3 is asking us up here, what is the temperature of the object 5 hours later, or 5 hours after the initial exposure? So we want to substitute t in to be 5, now that we figured out what the k constant is and what is the c constant. So now we're able to find out what is the temperature. So let's plug in 5 into our value for t, and then since this is entirely a constant, then we can multiply that all out to get 5.68119. So now that we have the natural log of t minus 90, which is approximately 5.68119, then we can use the properties of logarithms, which we get t minus 90, which is approximately e to the 5.68119, and add 90 to both sides. So therefore, the temperature would be approximately 383 degrees, 0.3 degrees Fahrenheit.